All right, we're going to look at a single example here and do all the different parts of it. It'll take us a few minutes. I forgot to mention last time that the things we're looking at here, L4 and R4, these are called Riemann sums. When we use either left or right endpoints with a fixed number of triangles, the idea was created by a Swiss mathematician named Riemann. I do not remember his first name, and it's not really relevant. So we're going to look at a single curve, y equals x squared, on an interval from 1 to 3. So we're looking for the area of that area. We're looking for the area of the region underneath the curve. First thing I like to do is to get a guesstimate, because that way I have an idea if my process worked and I got something that was reasonable. So I'm going to look at this and say that area is relatively close to a triangle. And if it was a triangle, it would have a base of 2 and a height of 9. Right? The value of the function there is 9. So I'm going to guesstimate that it's fairly close to 1/2 times base times height, which is 9-ish. So I'm looking for an answer somewhere near 9. Now, of course, you're thinking that this isn't a triangle. This top is curved, and it's curved inward. So our actual value should be a little short of 9 because of that concavity there. To find L4, we're going to break this up into 4 rectangles. Same width for each of them. So we got 1.5 and 2.5 there as important numbers, and 2 in the middle. The width of each of these rectangles is the same, and it's going to be 1/2 unit, right? 3 minus 1 is 2, divided by the number of rectangles there are. So it's going to be 1/2 for the width. The height of the rectangle is going to come from the value of the function on the left end. So the first one is going to be 1, and the function is squared, so 1 squared, plus 1.5 squared. The left endpoint for the third rectangle is 2, so 2 squared, and then 2.5 squared is the height of the third one. I neglected again to actually work these out ahead of time. I apologize, but I think we can do this fairly quick. 1 squared is 1. 1.5 squared is 2.25 plus 4 plus 6.25. Okay, 6.25 plus 2.25 is 8.5, 9.5, 13.5. So 13.5 divided by 2 is going to be, what, 6.75? And that is going to be an underestimate, right? Because we were taking the height of the rectangle on the shorter end. So we found the area of these rectangles here. And we want it to be less than 9, so that's good. I'm happy with that as an underestimate. Now, if we do R4, we can save a little bit of time here. We don't need to redo a lot of this work. If we use the right endpoints, we're going to need the value of the function at 1.5. My own handwriting is confusing me. 2.5, 2, and then at 3. Now, those are going to be the same numbers as these, except we're going to lose the first one, right? Because we're not going to be using this as an endpoint, and we're going to pick up the other end. So we're going to get 2.25 plus 4 plus 6.25 plus 9. And it's pretty easy to see that we've lost a 1, we've picked up 9, so that's going to be a total gain of 8. So that's going to be 21.5 over 2, which is going to be 10.75, I think. Of course it is, because if we picked up 8 and then we divided by 2, our gain would be 4. So that's 4 more than that. All right, so that's an overestimate. We know our answer should be somewhere around 9. That's a little bit bigger than 9. Then I want to average these two together. Just add them and divide by 2, or in this case, it's going to be real easy to do because halfway between 6 and 10 is 8. So we get an even better estimate by averaging those together of 8.75, which is very close to our guesstimate of 9. And a way to think about that is if you were to take these little errors here from our rectangles and you were to like cut those in half with straight line segments, that's the area you'd be finding is of those trapezoids. And that's going to be real close to the area of that curved portion. The last thing I want to show you is how to find the actual area or a decimal approximation for the actual area using the calculator. It's a real quick and easy process. You just turn calculator on first, put in x squared, and get your curve. All right. And if you want the area under that curve over an interval, you do second calc. Down here is the thing we're after, and I'm going to talk about that in the next video, that symbol. It's the integral symbol. So we choose that. So second calc, and that's option number 7, or you can arrow down to it like I just did. And then you put in the lower limit and enter. And here we were going from 1 to 3. So our lower limit's 1, enter, then 3, enter. And it'll do two things. One is it will actually show you the curve colored in, the area that you're finding. And down here, it will give you the value for the area, which comes up to be 8.666. So like I said, because of the concavity here, it should have been a little bit less than that, and it is, but only by about 1/6 of a unit. So this is a very accurate method using the left and the right Riemann sums, averaging them together. Check it on the calculator, and always try to guesstimate it first. Be back soon.